Okay, there we go. Gotta remember to turn the microphone on. I think everything should be good now. Okay. So, let's begin. Maybe I'll pull up an Inkscape. I actually posted it just now, because I needed it to transfer, so it's actually there now, on the GitHub. Let's see here. Can I pull up the link really quick? Here it is. So, okay, good. So today, basically what ended up happening was, and still is actually, I need to call them as soon as I'm done with class. You know, I had a flat when I came home from Monday's lectures, and I didn't realize it until very late on Monday night, so I didn't go to get it fixed until Tuesday, and then of course then they didn't finish. They didn't fix the tires, so now my car has 3 wheels because the spare is also flat, so we'll see. I'm gonna have to get it all back today, so that it'll all be ready for next week. So that was a disaster that I just did not expect. But all right, let's get back to let's get back to this. So what were we doing last time, right? We were doing binary search tree stuff. So let me show you. Let's just talk about it for a second. Let's say we were doing, binary search trees. And what are the operations that we did with a binary search tree? We did insert, right? And we did the iterative, right? Insert with a while loop. And we've done insert recursively, right? So we've done those 2 things. And then we've also done maybe a find method, right? We've done that kind of iteratively with a while loop, though we can do it recursively. And then we talked about remove. And remember, in order to do remove, basically the process for remove is to find the node you want to remove, and then you find that node's successor, and then you remove that node. Or I'm sorry, you should I say? You move the value from the successor to the node that you want to remove, and then finally you delete the successor. And this is a recursive call, right? To the delete method or whatever, right? So, or to the remove, I should say, yeah, you remove successor. Because delete might imply that you just delete the node, whereas remove implies that you're actually doing this whole process again. So that's the general thing. So this is the process for remove. Let's draw out some stuff. So let's just do an example, and then we'll code it up. And then maybe I'll talk a little bit about traversals. And then we will talk about the project, maybe, project 2. Oops. Okay. So here's a little tree, I guess. Let's put some more nodes in. Can't really fill up the next level entirely, but let's fill up some more stuff here. Let's put a node here. And then let's connect them up. Okay. So even without numbers in this thing, let's put some numbers in. Let's say we have, say, 50, and then this will be 23, right? Gotta move it up to the center. This one will be 14, 15, 14. I never know what I'm going to type when I type. Let's see, 31, 28, and 43, right? Something like that. Then here we have 67, 63. Hello, everybody. 81, and or something. I guess this has to be like 65 or something. So, okay, good. So now what happens if I want to, say, delete the root, right? So now I want to remove the root. And so finding the node is easy. Or I guess even if I want to remove, say, 67, right? I think it's about the same. So if we want to remove 67, right, the first thing that we want to do is we want to find the successor. So this is the node that we want to remove, right? We want to remove this one. And so this one here is the successor. So I'll make the successor blue. Let's make it sky blue, right? So this is the successor. Actually, no, it's not. It is not the successor. Successor is, let's define the successor. It was this. It is the successor of the root, like I wanted it to be, but I changed the node that I wanted to remove. So this is the successor, right? So actually, this is the new successor, and the reason is because it's remember what the successor is defined as, is the largest or smallest node, I should say, in the right subtree, right? So in order to find the successor, you go right, and then you go left as far as you can. And that's it, right? So in this case, what we're going to end up with when we do this deletion, I probably should have deleted the root, but that's okay. I can always copy paste. So actually, why don't I do that now? There we go. So what you're going to do is you're going to move this up to here. So 81 is now in this position. 67 is now out of the tree, and then you're going to remove this node here. Of course, this node is a leaf, so if you're going to delete a leaf, you're good, right? Just remove it. So, okay. So there we are. So basically here, all we have to do is just remove this node, and that's how the delete works. And then the important thing here is just to kind of double check to make sure that the thing that we currently have is a binary search tree, right? Does it still follow the properties of being a binary search tree? And the answer is, well, everything over here is still a binary search tree because we haven't touched it. Everything over here, like the 63, 65, that's good. Is this 63 less than 65, or 80 less than 81? Yes. Is 50 less than 81? Yes. So the point is that 81 should be the right child here. 63 should be the left child here, and all of those things are correct. Similarly, like, let's say that we wanted to, instead of remove this one, let's remove the root instead. Let's color it red for... And so this is no longer the successor, right? This is not the successor anymore. It's the one I wanted it to be in the previous example. So if you're going to remove the root, right, what are you going to do? You're basically going to look for the successor, right? And so you go right to 67, but then you start going left, right? And so as far as you can generally means a while loop or some kind of recursion in order to find as far left as you can go. So, but in this case, the successor is just this node here. And so since the successor is just that node, we can delete it, or we can remove, well, okay, let's be much more careful about what we say. What do? We transfer the value from the successor to the root, because that's the node we want to remove. And so we do that, so we'll go 60, whoops, got the bubble and not the number. So 50 gets popped out, 63 goes in. But then basically what we have to do is, remember at this point we have to recursively remove the blue node, right? Or the teal node, or whatever that color is, a light blue, sky blue. And so in order to do that, you also have to find its successor. So this is a recursive call to a delete function. So basically you'll say, okay, I'm going to call the delete function again on this node. And so then I'll find the successor. The successor to this node is the yellow node now. And so then you move this up like this. And then you just, now that the yellow node is a leaf, you can delete it. Like that. So, and again, we kind of want to check, is this still a binary search tree, right? So that's the question in the end, right? We always want to know, is this still a binary search tree? If it is, then we're happy. If it isn't, then we're less happy. So we check it and we say, well, okay, is everything on the left side here still less than 63? The answer is yes. The reason why that's true is because we took a node from the right side of the tree, right? So everything on the right side of the tree was already bigger than everything on the left side of the tree. So this is going to be okay. This one here has to be okay. How about the other parts of the tree? So is 63 less than 67? Yes. So that's why you should go right. Is 65 less than 67? Yes. So you go left. Is 81 bigger than 67? Yes. So you go right. So all of this structure over here is still binary search tree structure. So the answer is yes, this is still a binary search tree, right? So it's not exactly like rotations or rebalancing. Exactly what it is it's trying to do the minimal possible operation to remain a BST, right? So basically we don't want to do a huge amount of tree surgery, I guess you would call it, in order to basically keep the BST properties. So that's kind of the idea here, is that you sort of the tree remains a binary search tree. So that's good. Okay. So I think that's it for drawing things out. I think we've basically talked over, I mean, of course we did this last class, so it's not like this is completely new. But, okay, so let's look at how to code this type of thing. So how do we code this? Let's go to some code. So I've copy-pasted all this to my home computer, so I'm not even sure if it actually still compiles. I just did this right before class, so let's find out if this compiles. Fatal errors. It does not. It does not. There are errors in this. This if statement is a syntax error in a file that we actually don't need, but I have in this random project. So elevator. Oh, more elevator errors. Should I? Let's see. Should I remove this? Can I get it to not compile this? I'm not sure, because I don't want to fix any of these problems. What's the problem here? I don't really want to fix any of this, right? Because this is not even the problem. As you see, I definitely finished my implementation of Project 1, by which I mean I did not finish my implementation of Project 1. So, okay, any more things that we can do here? What is this problem? Must return a value. Okay. I could just delete the whole thing. I'm considering it at this point. There we go. All right, so that fixed it. Now we don't have to look at that anymore. Okay, good. So now I think we can like insert 5, insert 20, insert 30, insert 40, right? Insert 50, and what is it? Exit? Yeah. Okay. So notice that if you insert everything into a tree, a binary search tree in ascending order or descending order, you actually get this kind of like right tree, right? So the thing that we get here is a tree that starts at a root of 5, goes to 20, goes to 30, goes to 40, goes to 50, and so those are all children, right? So there's no optimal search property here. Like you get O of n search time because it's if you do something like this. So it's actually this is one of the kind of bad conditions that you could have when you're dealing with a binary search tree. Okay, maybe we'll see out something like just like something to indicate that there's actually a command to be input, right? So that it's not just a completely blank screen. Okay, so now let's implement the remove method, right? So I think we have it here. So here's remove. Where is remove? Here's remove. So let's, so I think we know already we'll basically need a, what are we going to need, right? We know in order to write this function, we're going to want a find node function that actually returns like a BST node pointer, and we're going to want a successor function that finds a successor, right? So basically, the reason why we want that is because note that find here, like this public find, only returns like a Boolean. So because it only returns a Boolean, the problem with it is that it's not going to give us the node that we want. So let's make some helper functions. So what are the helper functions that we're going to make? Let's make a BST node data type pointer find node, and we'll say data type value, right? So this will find a node with that value, and then what else do we want? We want a something where we can get the successor, like get the successor, maybe, of a BST node data type pointer p node, right? So we want to find the successor of the node. Keep in mind that if we you know what? Because this is my own code, and because I feel like doing this, I'm going to do something a little bit squiffy, but this is definitely not something you're actually going to have to do for a project. But what I'm going to do is I'm just going to say, I'm going to create a struct. This is like old school. This is really old school stuff that I'm going to do. But you see this in mega old C code. But I'm going to do it because I want to. Is that a good reason? Oh, look at that BST node. I never fixed that bug because I just blasted past it so fast. I never did that. So now, what the heck am I doing here? So I know it might seem a little bit bizarre, but I'm creating a struct. The only purpose of this struct is to have two elements in it. The elements are going to be pparent and pnode. The reason is because when I don't actually want to just return the node itself or the successor itself, I want to return its parent as well. And you'll see why, because we don't have parent pointers here. So because I don't have parent pointers, basically the way to argue why this has to be done is think about it this way. Like if I'm going to remove a node, right? If I'm going to say delete this 43 out of the tree, and we see that it's a leaf, right? We look at this thing and we say, this is a leaf. Now, how do we actually delete it out of the tree, right? The one thing that we can't do is we can't just say, oh, okay, unattach it and delete the circle, right? Because this little line is still there. Now, what does this line represent, right? This line represents the pointer from the parent, right? So the thing is that we can't delete this node unless we also tell the parent somehow that, hey, we're deleting one of your kids. So we have to be able to do that. And so that's kind of why I'm doing this. Obviously, one of the other solutions to this is just to actually, inside every one of these BST nodes, if you put in an extra thing where you say something like this and you say p-parent, right? That's another solution, but I haven't implemented any of that, so we're not going to go down that path. We're just going to, as we do finds and as we do get successor, we're just going to return not a BST node, but a BST pair. We're going to return the parent, and we're going to return the node itself. Technically, we don't even need the node itself. We can always find it again, but like we can just check the two children and be like, which of you is the right node? But I'm going to return that just to be nice. Okay, that's all I think that's it, right? That's all we need to really talk about in terms of that. Yeah, so let's see here. Let us create the two helper functions. We don't want that tool. We can create this, and we can create, oops. Yeah, we could always just return the parent. As I said, we could do that. But I want to return both nodes. So the reason why I want to return both of them is because if I was thinking about that, and the problem is if you don't, I guess the question is, so here's the thing. Here's what I was thinking about. What if the node we want to find is the root, right? So if it's the root, then we find that node, but it doesn't have a parent. And if it doesn't have a parent, then we set the node itself to the roots pointer, and we set the parent to null. And so actually what that does is it tells us even more information. It tells us that we're at the root. So, yeah, I guess there's like one exception, but okay, right? Who cares, right? So, yep. So I think that's generally why I want to make these silly data things. Yeah. So anyway, so let's just find the node itself. So let's say BST node pointer p current equals p root, right? And what we'll do is we'll say while p current is not equal to, or while p current, right, m data is not equal to value, right? What we'll do, and I guess we also need to check while p current, right? And so what we'll do here is we'll say we will create a BST pair because we need to return one regardless. Result, we'll call it, and maybe let's make a default constructor for it just so that we can feel safe. You know, just a little default constructor that sets these both. Like that. So, you know, that'll just save us from any kind of unfortunate accidents that we might have because we didn't think hard enough about what to do. So, okay, and then here we'll have, currently, I guess we'll need, actually, you know, we can't even do that. Well, no, we shouldn't do that yet. So we'll do p-parent is equal to, say, null pointer, right? And so currently the parent pointer isn't going to actually do anything in this function. Basically what we're going to do here is we're going to say if, you know, p-current, whoops, dot m data, if value is less than it, then what we're going to do is we're going to set p-current equals p-current dot p-left. We're going to set p-parent equals p-current. And then else, I dislike that Java style of else. There we go. So that's all we really have to do, I think, in order to find it. So I think the thing here is, if we have to think about all the possibilities, right? Like, what if we don't find it? So what if p current is equal to null pointer? Basically, we get all the way down to a child. So then what we do is we just return. So we say if not p current, right? We return result right now. Else, right? So else p current isn't null. We set them, right? So I think this is why I didn't want to just. I was thinking, like, couldn't I just use the variables inside of result to find it? And the answer is I don't want to do that. Well, actually, no, we could. We could actually do that. So what I mean by that is that we could say, instead of using these two variables here, we could actually just say result.p node here, and we could say result.p node. Some complicated nonsense, really. I guess I should use the refactor, but I didn't, so I'm just going to copy paste really quickly. And then here, this is going to be result dot p parent like that. And this will be result dot p parent. And this, are we done? We can delete these now? I think so. Yeah, we can use the variable. So the point is that if not p current, that just means we didn't find it, so then we should just set result.p parent equal to null pointer just in case. Right? And then what we'll do here is do result dot no, we're done, right? Yeah, in the if statement. What about it? I think this is right. Isn't this good? This will do good. It's kind of a weird find node function in the sense that yeah, okay. Good enough. Oh, do I have a p current left? Result of p node instead of p current. Yeah, if I have any p currents left, then I want to get rid of them. I don't see any p currents. Ah, here. Yeah, you're right. There we go. Okay. Yep. Okay, good. So, yeah, this is a little bit odd, but sure. There we go. Okay, good. Cool. Yeah, so I think that's a good find node function. That'll get us what we want. Yeah, yeah, so there's a delay probably. Anyway, yep, so I think we got this. So that's what we want here. So now we should write our get successor function, right? So the get successor function, do we need to return? Oh, did I have a spelling error? Oh, yep. Okay, cool. All right. Okay. So, cool, good. So let's get on to the get successor function, right? So, let's see here. What do we do for get successor, right? So the answer is we go right, and then we go left as much as we can. And I don't know if we actually need the BST pair for this. We'll see. We'll see. Maybe we don't even need it. Maybe we can just return the successor. Well, I guess the only reason why I want it is because if we have to delete the successor node, we'll need its parent. So, and we don't want to refind it. So actually, no, my previous thinking was correct. We shouldn't get rid of the pair business. So return result. Okay. Cool. So, what do we do here? So the answer is, whatever p node we're on, right? We'll say result.p current, no, p node equals p node. Oh, I'm sorry, no. Dot p right. There we go. And so I'll explain what I'm doing in just a second. Basically, what I'm doing is I'm saying the node we're at is the parent of the successor, at least to start. And the successor is the right child. Now, of course, this might not stay because obviously if right, so we do, again, yeah, so we do have to check if we can go right. So, maybe we should even check, yeah, so, I mean, maybe the user, the programmer, or maybe we give ourselves a bad, node, so we should probably check it p node. Otherwise, we could end up with a seg fault or a null pointer or something like that. Now, presumably, as long as we're not completely insane, which of course we might be, we won't pass a null pointer into this function. We'll only ever pass the node that we found, and hopefully that node we check is not null pointer, but let's just put an extra safety check in here. There's nothing to be hurt by it. Okay. And I mean, we shouldn't be passing a null pointer into this function, because if we do, then that means that we are trying to delete a null node. Anyway, but yeah, again, it's a good thing to put the safety check in, just because otherwise, you know, it's always good to try to avoid a segmentation fault or some kind of problem like that. Okay, so now we basically just do the same thing. Actually, I think we can almost just copy paste the code, right? Almost. Well, actually, no. Well, we can copy paste the code because it's easy, but actually we want to do even less than this, right? Result.pnode and result. Yeah, I mean, this isn't exactly what we want. We want to say this while there's a left child, and then we basically, I'm just, okay, I need to steal way less than this. This is all I need. Yes. I think this is all I need. Basically, while there's a left child, you will go left, right? So we never actually go right again. So this is going right once, right? So this is go right. And so this is go left until you can't. Right? So this is the I think this is fine. Result.pnode.pleft, and we do check if pnode, but here result.pnode is pnode.right, so actually we do want to check if the right is something. So I guess we also want to say result pnode, just because if the right child doesn't exist, I guess we could. This is fine. This is fine. Okay. So, all right. Good. Good. Now let's pretend this works and move on to our remove method. So the right answer, of course, when you have things like this, are to test them out first, right? Test these out to make sure they work. So maybe we'll even make them, let's even make them public for now, just so that we can run some tests on them, maybe. And then what we'll do is make them, like, once we don't need them anymore to be public, we'll make them private. During development, we can make them public, just because they're, the reason why we probably don't want to make them public in general is because if you return an actual BST node pointer, then they can't really mess up that node, but they can mess up that node's children, right? Or if you pass a parent, if you give them one of these pairs, then they can actually mess up, they can't mess up the parent, but they have access to the entire, and by they I mean the programmer who uses this structure then has access to essentially the subtree that starts at the parent, and that would be kind of bizarre and not so good. So, you know, because basically we would know what's going on in the rest of the tree, but technically they would have this pointer that they could access and destroy like a part of our tree, and we wouldn't really know it, and they could change pointers on us and cause problems. So let's not do that. So okay, so the first thing we want to do is find node, remove value, right? There we go. And then of course what did I do? Where am I? Here okay. Sorry about that. I accidentally hit page up or down and then got lost. But let's say BST pair, let's call it pair equals find node, something like that. And so then what do we do after that? So then what we basically have to do after that is, well, I guess we have a find successor method, right? So we have to find the successor of not the, so I guess there's a bunch of edge cases, right? So what if the thing is the node we want to remove is itself a leaf? Then we don't need to do anything, right? So we don't need to find successors. We don't need to go about the whole process, right? We can just remove it. So so let's see what happens, right? So if remove pair, maybe we'll even oh, have I been doing that wrong the whole time? Yes. Oh no, but I return a pointer. So I should just return, I don't want to return a pointer, I just want to return this. And I don't want to, and so this is what I want to actually do. Huh. Yep, so they're not actually, we don't actually want them to be pointers, because we actually don't care if they have to copy, right? Just make a copy of those two pointer values on the return. So, yeah, oops. Is that fixed now? Maybe. And then here, same thing, same thing, same thing. Result. I'm probably gonna miss one, but it doesn't matter. We'll just fix it post. Yeah, I got, you know, I'm so used to pointers that when something's not a pointer, I'm like, hey, what's going on with that thing? I don't trust it. Yeah, I don't actually want those to be pointers. I just want them to be values. There we go. Better. Okay. So did I fix the, yes, did. Result dot. I think I fixed most of them. We'll find out if there's a problem. It'll tell us. So, p node, right? So, I guess the first thing we have to check, so maybe before we even check that, there's, as I say, there's just a huge number of edge cases, right? So, what if the node doesn't even exist? What if the value doesn't exist, right? Then don't do anything, right? So, first we want to check if the node exists. So, if not this, then we can just return false, right? Like we didn't do anything, right? So that's just didn't do anything. Return false. No removal. Okay, so now we did find the node, right? So after this, we found the node. Let's return true here now. So after this, we found the node. What are we gonna do? So we're gonna say, what if it's a leaf? Right. So that edge case will probably, it'll be nice because it's also kind of the base case of the recursion. So we don't want to be just recursing down to delete this thing, because if we, so I guess we do want this edge case. So we kind of want this edge case because if we don't have it, we'll end up kind of recursing again, right, to delete a leaf. We won't find a successor, and then we'll have to handle the edge case there, right? So pointless, right? Let's just do it now. So let's say if not remove pair, no, so what do we want to do? So if, if not remove pair, dot p node dot left, and not remove pair dot p node right. So this checks to make sure, right? What this is doing is it's saying, is this one null and this one null, right? So if both of them are null, then what we can do, and this is one of the great things about having the parent value, right? So now what we can do is we can say, now we can delete, right? So now we can delete the node and kind of fix the parent value, parent's pointer, I should say. So let's do that. How do we do that? Good question. So I guess we say if remove pair. So I don't tell you which one it is. I guess we could even, technically, if we're even nicer to ourselves, we could, but it doesn't matter. Remove pair dot. Well, okay, so we have yet another edge case. So I'll deal with that edge case later. So let's deal with this right now. So if you're the left child of the parent, right? So if you're, what does this mean, right? If the parent's left is equal to me, then what we can do is we can set remove pair dot p parent dot p left equal to null pointer, and then delete remove pair dot p node, right? Cool. I guess we can move this out. We don't need to have that inside the if statement. Else, I really hate that Java style else. I know it's all the very popular nowadays, but I hate it. Okay, so I feel like this is basically what you do. If it's equal to the parent's left, then you do this. If it's equal to the parent's right, then you set this, and then you delete that. So there's one slight problem here, because obviously, what if the parent is null? What if we're at the root? So if we're deleting something that is a leaf and we're at the root, that just means that we literally have exactly one node. So we have yet another edge case, right? So if remove pair dot p parent, well, if not, so what we're going to do is we will say delete p-root, right? And then p-root equals to null pointer, right? And then what we'll do is, basically what this means is that the node is equal to the root. So you can either say if the parent is null, or you could say that remove pair dot p node is equal to p-root, right? Because there's only one node in the tree without a parent. If there's two nodes in the tree without a parent, then you're in some serious trouble. So then we return true, just so that we don't accidentally fall into this stuff here, right? Okay, so this takes care of the leaves, right? If the leaf is the root, we delete the root, set the root to null pointer. If it's not the root, we will remove it and then delete that node. And remember, we basically set its parent to null pointer and then delete the node. Or I'm sorry, the parent's child pointer, not the parent itself. We said the parent's child pointer, and we just have to figure out which one that is. So either the parent's left is equal to the node, or the parent's right is equal to the node, and so those are the two options. Okay. What else? So notice that this has all basically been edge cases, right? This is like the leaf edge case. This is the if we don't find it edge case. So let's actually get on to the actual delete case. So now so this is actually what delete is, right? Or remove is, right? So now we're going to find the successor. And the reason is because if the thing is not, if we find the node and it's not a leaf, then we have to do the successor business. So let's do that, right? So what we're going to do is go est pair successor equals, maybe we'll call this successor pair equals find successor. Did I also not forget to do that there? Yes. I always forget those things. Or, I don't know if I always do. It's been a long time since I've written a template class. So yeah, I guess it's not really reasonable to say I always forget something that I don't really do all that often. But anyway, let's see here. Result, is it find, wait, what did I call the thing? Remove pair dot p node, right? We want to find the successor to this node. So, and then what we're going to do is we will move the value, right? So I guess here we can also return true so that we bump out of the function here. So now we're going to find the successor. And so why does a successor have to exist, right? Well, actually it doesn't. So if, let's see, successor dot p node, right? So we need to check to make sure the successor exists. But if the successor exists, and then there's the else case, then what do we do? So if the successor exists, then we're going to copy the value, right? So we go all the way back to how we did this in the beginning. We're going to copy the value. So we'll say remove pair dot p node dot m data equals successor pair dot p node dot m data. So we copy the data up, right? And then what we do is we call, I guess we can return remove. All right, what do we want to call? Technically, well, I think we might even need more helper functions, but let's call a remove node function on this, right? So this is going to be that. Actually, we probably should just pass the whole remove pair into it. Because if we're going to remove a node, we should have its parent. Okay, there we go. And so we'll, no, actually want to pass in successor pair. That's what we want to do. Why does it, the value is never used? Well, actually, the value, well, who cares if the value is never used? The whole point is that it's fine. Okay, so that is that part. And then remember that there's the other case, right? Where, so there's the weird case about trees where if, say, we have something like this, let's uncolor all these nodes and just see which one. Let us say that we are going to delete 67 now, right? And 67 doesn't have a successor, but it has a left child. The answer is that we have to basically relink the parent, right? So we have to basically do something like this. We have to say, like, we have to like relink this parent here to here, because we're going to get rid of and then delete this one, right? So that's basically how you have to do it. Just make sure that you don't accidentally delete this one. So okay, let's see about how we can do this. So yeah, if we wanted to, okay. So else we're gonna do something like that. So if there's no successor, meaning that, then what we're gonna have to do, right? So there's no successor, but there's a left child, right? That's the case here. So no successors but left child. So if that's the case, then what we do is we say remove pair dot p parent dot, I guess, well, we have to check to see which one it is. So if, technically, I think, right, dot p left is equal to p node, then what we'll do is we'll say remove pair dot p left equals what would we say? We would say something like remove pair dot p node dot p left. Right, so there's a left child but no right child. Okay, there we go. And then we have to delete p node, right? And so then what we're also going to do is else. So now it's a right child, right? So now it's the parent's right child. So now we'll just copy paste this code. Technically, we can move the delete node out of there because it's double coding inside of an if statement that we don't need. Keep in mind that it's still left, right? On this side, it's still remove pair.p left. So I think that's right. I think that's fine. And of course, there's yet another problem, as usual. What happens if there's no? What happens if there's no parent, right? Or what should I say? Yeah, what happens if there's no parent? I.e., if the thing we're removing is the root. So if remove pair dot p node equals p root, then what we're going to want to do is just set, I guess we'll have bst node. Well, okay, so what we'll do is we'll say p root equals p root dot p left, and then we'll delete remove pair dot p node, which is still keeping the old value, and we'll return true to get out of this statement. Okay. So that is removal. So there's a lot of edge cases here, right? There's a lot of little details that we had to think of. And of course here, I even had to use another method that I haven't implemented yet. I guess we do check if it's the root at the top. If it's the root, no, we check, so it's the order of checking, right? So here we know it's a leaf that's also the root, but we don't check if it's not a leaf, it doesn't go in here, which means that if it has a left child, it doesn't go in. So yeah, I mean, maybe we could check if it's the root, and then, but you know, it'd still take an if statement, like if it's the root and there is a successor, and if there's a root and it's not the successor. So it would be a different kind of breaking up of the if statements, I think, right? Because in one direction, you would have the if statements break up one way, and the other way. I don't think it really matters. Of course, as I say, I am using a function that doesn't exist, which is great. Which means we have to implement this function, right? Wonderful. Actually, what we're going to do, the secret trick, is that this is actually going to be the remove node function. And it's going to take a BST node, or BST pair, remove pair. And then we're not going to search in this function, right? What we're going to do is we are going to take that, we are going to do this, we are going to create a remove function, we are going to do this, and we're going to say, what is the original thing? Like data type remove value, something like that. What we're going to do here is find the first node, right? And then it really doesn't matter. We don't have to do almost any safety checking. We're just going to return remove node, remove pair, like that. And that will do it. So we'll find the first one, and then the rest of them we're not finding, because the rest of them on the way down the successor tree is just find successor, find successor, find successor. So the only time we actually have to find a node is the first time. So that's why we'll have this function be this, and then we'll have a remove node function that is this. Now, of course, technically there's a lot of, I don't know, we could make that a reference or something like that, but it doesn't matter. Just the reason why it doesn't matter to me is because we are essentially just copying a lot of these values, right? We're just copying some pointer values when we create this thing. I guess we do need a data type in here, right? That's fine. That's fine. Okay, so now the question is, does this work? And the answer is almost certainly no. But who knows? I mean, I think we've dealt with a lot of edge cases. We've thought of a lot of different things that can happen. So maybe it'll work. Who knows, right? It's a big mystery. So yeah, let's try it. Let's test it. So yeah, got it. Okay. Okay, so let's say that this is the code that we're going to run. Is the thing currently running? No, thank God. Okay, so first thing, I mean, right, the first thing is, does this work? Does it compile? It might. No. It does not compile. Okay. Error. Identifier not found. Oh yeah, I knew it didn't like this. Why didn't it? Oh, because I used the get successor. Get successor. Try again. Error. P node. So it has to be remove pair dot. And let's go. Keep moving. Right. Okay, wow. Okay, so insert 5, insert 2, insert 10. All right, let's remove 10 just to see what happens if we remove a what are we removing? Data has not been found and not been removed. Nice. So it doesn't work. So the question is, why doesn't it work, right? Let's say remove 5. Data has not been found. Remove 2. Remove 1. Okay, yeah. So remove just does not work. So let's check it. Let's check it. So the first question is, does it find, right? So is it finding the node, right? So let's check to make sure it is. So if, let's say, remove pair dot p node, we'll just see out something like see out node found, right? Else see out node not found. We really should have tested our find node function, which we did not do, but now we're going to test it. So let's test it, and let's say remove. Oh no, we got insert stuff. Insert 5, insert 10, insert 2, insert 15. Remove 2. Node not found. Good. So the problem is in the find method. Why? So, I mean, That's funny. What'd I do? What'd I do wrong? Um, hmm. Oh. uh, yeah. Yeah, I remember I deleted, I was creative, right? So this is the creativity uh, and ingenuity will be punished, right? Because I deleted, I was smart initially, and I was like, I'm just going to do the boring thing, which I know will work, and I set the things, and then I deleted all those variables, and then just never did that. So, okay, yes, so that's what happened there. Let's try again. Okay, now let's remove 2. Oh. Okay. Let's remove some more leaves. Remove 20. Remove 15. Alright, so that's... Wow, that's funny. Okay, I expected the problem to be way more horrible. Let's insert, say, 2, insert 1, insert 3, insert 4, insert, say, -1, right? Insert 2 again, something like that. So now let's delete. So now is the big test, right? So if we're going to delete, let's say if we're going to delete 2, actually if we're going to delete 5, right? Let's try a root remove. Let's say remove 5. So what's going to happen here? So remember that this is the right subtree. So actually the successor is just 10. So it should pull the successor up into this node. And then, I mean, probably what it's going to do is just segfault. But if it works correctly, then what it's going to do is pull this node up into this place. And then there won't be a right child. So let's see. Okay, it did. It did. Wow. Oh, here's an edge case that... Did we think about this edge case? Where there's no successor, but we're removing the parent. We did. We did. We thought about it. We actually did it. I didn't think we did it. I thought we didn't do it, but we clearly did it. Ugh, that's ugly. I hate that. This -1 should be here, but so for some reason the tabs got all messed up. Yeah, so let's try to remove, let's say, you know what, let's exit, let's restart the whole thing. Let's restart. Ah, you see, this worked. Amazing, right? I mean, hey, that's pretty good. Certainly did not bet on that. Certainly bet against myself on that one, right? Let's make a big tree. I really hate how it's doing that with tabs. I'm not sure why. But, it doesn't really matter. We know where the 5 is. The 5 is the child of 13, even though it's kind of warped here. Yeah, I bet it has something to do with, like, the line return interfering with something ASCII-ish or something. Let's insert 75, insert 211, insert 321, and then, remember we want to insert some stuff like 72. Oops, I hope this doesn't break it. I didn't. Insert 67, insert maybe 98, insert 62, insert 69, insert, let's see, 82, insert. I want to make a big tree. The reason why is I want to remove a node. Yeah, yeah, it probably has something to do with this like space interfering. Yeah, it's some nonsense with the ASCII and the line returns and stuff like that, but it's not a big deal. It's of all the problems that we could have with this thing, right? A little bit of ASCII nonsense is not the problem we should be worrying about. Which of course is why I worry about it. So let's see here. How can we get something to insert on that side of that tree? So 75, it has to be bigger than 75. Well, okay, let me see. Okay, so what happens when we delete remove, say, what happens when we remove 72? That's a good question, right? So 72, that's a good node to remove. That's why I wanted to make a big tree here, because if you don't have a big enough tree, you're not, like, the problem is if you only have a tree that's like 2 or 3 deep, then the problem is almost everything you're going to test is either deleting a root or deleting one intermediate node or deleting a leaf, right? So everything is an edge case. So that's why I need basically, essentially, at least height 4 or 5. It might have been boring to watch me create it. It was a little, probably, but that's not the point. The point is we needed a tree that had enough nodes so that we could run this. Now, I think the successor, if I'm not mistaken, is... Oh, wait, what is the successor of 72? Well, let's see what happens when we remove it. Oh, so there's no right child. So actually, it needs to move 67 up. Let's see if it does that. No. It explodes. So... basically, all of this but remove is already posted. But I'll repost the remove code. Of course, the remove code doesn't work, right? There's a slight bug in it somewhere, right? So something isn't right about it, because we just found a bug. So instead of debugging it, which, you know, would take a long time, let's see here. Yeah, unfortunately it exploded. But hey, it did a lot better than I thought it was going to do. So, you know, if you write this much code in the speed that I wrote it while you're talking about it, you're going to have problems, right? You're not going to just... If you get, you know, you're going to have issues. So let's see here. Where's the remove node code? So here's the remove node code. I don't know why I'm debugging it. I really shouldn't be. So we get the successor. There isn't a successor, right? So it shouldn't go into here. So then we say if it's the root, it's not the root. If it's the parents left, then we set this. Should be fine, right? That should have been fine. So something... So probably something in here too, right? This is kind of the right, or the correct code. It is what we want, in a sense. At least the words here kind of match, like, you know, you want the parents left to be set to the, you know, remove pair.pnode.pleft, right? So we want this to be set. So in some sense, we want to do this. We just don't want to explode. So we have to find out why it's exploding, and then fix it. Yeah. I guess you could ask at the end of class. Yeah, sure. So I unfortunately I don't have time to fix all of this, and so I'm gonna fix it kind of off screen and then post it again. Anyway, so and so maybe when we do AVL trees, I'll show you why, and I'll talk about AVL trees. I thought I was going to get to the project. I certainly will not get to the project. why it's better to have a parent pointer. Obviously, if we have a parent pointer, we can remove a huge amount of this nonsense. It actually cleans up. I never really realized how nasty remove is without a parent pointer, all the tricks that you have to do. I'm not actually sure if I've ever implemented a remove function without a parent like this. I'm actually becoming convinced now that I've never... this code is not familiar to me. This is like the first time I've ever written this. And there's a reason why. I don't want to do this again. Like, this is weird. I promise you that the code with the parent is a bit cleaner. What do I want to talk about now? What I want to talk about now is I want to talk about traversals of trees. So, because that's kind of important. So I want to talk about traversals. And so we've already kind of done some traversals, but I want to basically... traversals just mean walk the tree, right? And so it's always done recursively. Unless, of course, you talk about level order traversal or something like that, but we'll talk about that. Unfortunately, that's a little different. So there are 3 traversals that you can do of a tree, and those are pre-order, post-order, or I should say pre-order, in-order, and post-order, right? And so I think that in order to... So let's just look at this tree, and let me describe what a traversal is. So here's what a pre-order traversal is. It means print the node's value, or, visit the node. Then, recursively, visit the left child, and recursively visit the right child. And what I mean by recursively is, call pre-order traverse on the left child, right? And then you call pre-order traverse on the right child, right? That's what it means to say visit. So that's probably the better way to say it anyway, because visit implies, like, print it or something, right? Do a calculate, whatever. So whatever you're going to do there, so let's just take all these parentheses off. Yeah, so this is how to do a pre-order traversal, right? And so let's do the pre-order traversal of this tree. So the first thing we're going to do is we are going to and of course I've completely run out of time, but let's at least do the pre-order traversal of the tree. So we're going to visit the root node, right? And then we're going to basically visit recursively 23, right? So then we're going to call pre-order on 23, and then we're going to call pre-order on 67, right? And so then what's going to happen is that pre-order on 23 is going to evaluate into, right, 23 because we visit the node, and then it becomes pre-order of 14 and pre-order of 31, and then pre-order of 67 is still unevaluated. And then here what we're going to get is 63, 23, then we get pre-order on 14, which just evaluates on 14. It doesn't have any children. Pre-order on 31 visits 31 and then gets pre-order on 28 and pre-order on 43. And we still have pre-order on 67 sitting around. And then finally here we're going to do, well, not finally, we're going to do 63, 23, 14, 31. 28 doesn't have any children, so we just visit it. 43 doesn't have any children, so we just visit it. 67 we visit, and then we do the pre-order traversal on 65, and then we copy paste and we remove the p because there's no children. So this is the pre-order traversal on 60 on this tree, right? So this is how to do the pre-order traversal, and maybe next time I will have time to actually finish all of this. So yeah, if you have a question about the homework, I will hold some special online office hours tomorrow, I think, or you can send me an email. That I think the problem is that I have to run off and start a new live stream for my 201 class. It starts at 1, so I unfortunately don't have a lot of time right now. I'm kind of in a bind, so I don't want to accidentally not start the next live stream. Okay. Yeah, so what I'll do is I will post this document here as a PDF, and then I will repost when I get around to it. I'll repost the removal code. I will probably try to fix the removal code first. There's probably some very subtle bug in here, which is the reason why I don't want to fix it is A, because we're at -1 minutes in class, and B, because the bug is probably subtle, and if I tried to fix it, it could be bad. So, yep. Okay. I think that's it for now. I will see you all in person on Monday. I'm sorry that this happened. I am not happy about how this went. But hey, at least, you know, I have my backup plan, which is do the thing that I did during the online semester. So, that's what I did. Okay, thanks everyone. Assume functions for it, like, no. No. Don't assume that. Because there's a better way to do it. Okay. Alright, so that's it for me. I'm gonna have to run. Alright. Have a good day, everyone. Play the outro.